Hello and welcome to the STEM lab, and particularly the first floor level where this electronics laboratory, WPA 112, is located. This is one of our main undergraduate laboratory areas used by the WolfsonSchool. The experiment being introduced and demonstrated is a second year or Part B analog experiment, which is based around an semiconductor device known as an op-amp, or to give it its full name, an operational amplifier. It is the black square device made of epoxy, here shown with 8 pins, 4 down either side of the device. This experiment has been chosen because it uses a combination of both hardware and software. The hardware we're using has been manufactured by a company called National Instruments. They are a multinational company with their headquarters based in Austin, Texas. The actual product name Elvis is an acronym and is short for Educational Laboratory Virtual Instrumentation Suite, just in case you were wondering. Previous to this, the focus of this experiment was for the students just to take measurements on a mostly pre-wired experiment box without gaining any particular understanding of how the op-amp is used in a very practical sense. This experiment is based around the 741 op-amp, which was first developed back in the early 60s by Bob Widlar, an engineer working for Fairchild Semiconductor. This op-amp is used because its performance is now relatively poor when compared with modern devices, and hence its poor performance and flaws are more obvious to show. Interestingly, after designing a whole family of new op-amp devices, so the story goes, Bob asked for a raise at Fairchild, subsequently didn't get it, and so he quit the job. Here is the generic circuit symbol for an op-amp. You can see that it has 2 inputs here shown on the left-hand side and an output. Although the power supply connections are shown, they are usually omitted for clarity. The software we are using in this experiment is written in NI's own language, referred to as LabVIEW, and provides a suite of virtual instruments to support the Elvis hardware platform, here shown on the screen. This is a circuit diagram and shows the op-amp wired as an amplifier. It simply consists of 3 components called resistors, wired around the op-amp. This circuit is referred to as an inverting amplifier. Okay, so here we have the completed final wired circuit of our operational amplifier, ready for the power to be applied and the circuit to perform its duties. Here we have the op-amp now wired up and working in real time. You can see the input signal is the top green signal and the output is the bottom blue signal. If you look very carefully at the bottom, you can also see the measurements show that the blue output signal is 10 times the input signal. Also, that the signals are inverting. In other words, when the input sine wave signal goes positive, the output goes negative. Here on the PC screen you can see the function generator instrument. This provides us with the input sine wave signal, the green input trace you saw before. Here is the oscilloscope instrument. This is quite a useful instrument for engineers because it allows you to actually observe the waveforms. Again, this is all being done in real time, and this is a virtual simulation of an actual oscilloscope. One nice feature of using software and hardware is that integrating into one platform gives you the ability to be able to automate, record and log any of the experiment measurements along with the resulting data. One significant parameter of the op-amp's performance, which can be useful in circuit design, is that with increasing frequency, the op-amp's voltage gain significantly reduces, or as the term is stated, rolls off. It can be seen that if we use another virtual instrument to produce what is called a Bode plot, this is simply a graph of the op-amp's gain on the vertical axis against the frequency of the horizontal axis. All this measurement can be automated and captured. As you can see, this instrument has been set up in the NI Elvis environment, and you can see how easy it is for the measurement to be taken in real life when the instrument is run, and then you're left with a plot to finish. Not only that, but you can see that the measurement is quite speedy and certainly much quicker than it would take traditional students to do traditionally using standard test equipment and making each of those data point measurements manually. You can clearly see on the top plot how the op-amp gain falls with increasing frequency. Not only that, but every data point on this graph can be stored as a text file for later inspection or imported into a spreadsheet. Additionally, this software also provides cursors to further assist by inspecting any point along the graph, as can be seen when the cursors are enabled.